My name is Jacob Adamczyk, and I'll be presenting our work on reward shaping and compositionality in entropy-regularized reinforcement learning. To begin, I'll discuss some background information on reinforcement learning, which is a paradigm used to solve sequential decision-making problems. In RL, an agent interacts with a particular environment by taking actions. These actions induce state-to-state transitions, and the agent accumulates rewards by taking actions. The goal of the agent is therefore to maximize the amount of reward received. In order to optimize the total rewards collected, we have the following objective function. We have a discount factor gamma, which is strictly less than 1, and this ensures that infinitely long trajectories will have a convergent total reward. Therefore, our goal in reinforcement learning is to find a policy, which is a distribution over actions for every state, that maximizes this objective function. This policy, the optimal policy, will correctly choose the actions to maximize the expected reward. In the standard reinforcement learning framework, the solution to the RL problem consists of calculating an optimal value function, Q star. Here we can see that the backup equation or optimality equation for Q star involves a hard max or greedy max over all the actions. Once we have this optimal value function, we can calculate an optimal policy from it, which again acts in a greedy fashion so as to maximize the value at the next step. In the entropy-regularized setting, we add an entropic cost to the objective function. This ensures that the current policy or optimal policy does not stray too far from some prior policy. This means that the optimal policy will now be stochastic, which ensures that it's robust to perturbations in the environment and it's more amenable to transfer and compositionality. In entropy-regularized RL, the Bellman optimality equation changes. Rather than having a hard max, we have a log sum exp, and this Q function can again be solved through iterating a backup equation. In this work, our main goal is to study how prior knowledge can assist an agent in solving new tasks, particularly in the entropy-regularized setting. As a brief overview of our results, I'll first demonstrate how any two tasks with different reward functions can be related by a third auxiliary task. This main result leads to the extension of potential-based reward shaping to entropy-regularized RL, as well as an extension of previous compositionality results to nonlinear composition of tasks. This allows us to improve the training time and also allows us to improve zero-shot approximate solutions in the compositionality setting by learning a correction factor. In standard RL, we have potential-based reward shaping, which gives a way of changing the reward function such that the optimal policies are invariant. So one can solve the task defined by reward function R, or a shaped reward function, R plus gamma phi minus phi, and these two tasks yield the same optimal policy for any choice of phi. And this can provide the agent with some form of prior knowledge and possibly improve the training time of the agent. We would like to extend the results of reward shaping from standard RL to entropy-regularized RL. In order to do this, we want to consider how a solved task can be used to infer information about a task of interest. We show that there exists a third auxiliary task with a reward function kappa that is just a difference between R tilde and R. By solving this auxiliary task, one can connect the solved task to the task of interest. The optimal value function for the solved task and the auxiliary task can be combined in order to retrieve the optimal value function for the task of interest. In this way, one can instead learn the optimal value function for the auxiliary task rather than learning the task of interest directly. So we view this auxiliary task as a sort of correction from a base solution into the solution of an arbitrary task. Notably, the optimal policy for the auxiliary task is identical to the optimal policy of the task of interest. The fact that the optimal policy for the auxiliary task is the same as the optimal policy for the task of interest means that we have a form of reward shaping in entropy-regularized RL. However, we have to be a bit careful. The auxiliary task has a prior policy pi star, meaning that the prior policy for the auxiliary task has to be the optimal policy for the solved task. We can correct for this, however, and add a correction term to kappa that allows us to use a prior policy of pi 0, so that all tasks have pi 0 as the prior policy. This allows us to rewrite the reward function for the auxiliary task in something that resembles potential-based reward shaping. As a brief demonstration of these results, we can consider a solved task on the left, in which an agent must navigate to the bottom left of a maze. If we now consider a new task, which is defined by this middle section's reward function, the agent must now navigate to the right corner of the maze. If we use this previous knowledge to shape the rewards, we can see that the reward function becomes more dense. Now the agent receives rewards in places other than just the goal in the bottom right corner. As we can see, this introduction of prior knowledge decreases the required training time. This result shows that with prior knowledge, we can shape a reward function. However, we would like to have a potential-based reward shaping, which can be used with an arbitrary function rather than only an optimal value function. In order to achieve this, we use the recent results of Cao et al., who say that a reward function can be defined such that any function phi is the optimal value function and any policy pi is the optimal policy. This reward function has the following form. As a special case that simplifies matters, we can let pi, the optimal policy for this task, be pi 0. And moreover, we have a degree of freedom now in phi. This means that with a reward function of just 5s minus gamma times the expectation of 5s prime, we already have the optimal solution. The optimal solution is simply phi as a value function and pi 0 as the optimal policy. By using this reward function for our base task, we find that the auxiliary task has a reward function kappa that is simply the potential-based reward-shaped version for the task of interest. Therefore, from our result relating any two tasks in Entropy-Regularized RL, we've extended the potential-based reward-shaping framework from standard to Entropy-Regularized RL. We would now like to extend our results to the case of multiple solved tasks. Prior work has already shown that compositionality is successful in Entropy-Regularized reinforcement learning. This means that we can take multiple solved tasks and compose them efficiently to solve new tasks. As an example, an agent may have solved these two subtasks, A and B. The first subtask being that the agent must navigate to the very left of the maze, and this middle task B, showing that the agent must navigate to the bottom of the maze. We would like to compose these tasks in a way that tells the agent to navigate to either the left side of the maze or the bottom side of the maze. In order to do this, we could learn from scratch this new reward function, or somehow use this previous knowledge to improve the training time. In the previous section, we've shown how a single prior solution can be used to shape the task of interest. Now we would like to know how we can use multiple solved tasks to assist in the solution to a task of interest. We note that this task of interest, R tilde, just has a functional form where an arbitrary, possibly nonlinear function f can be applied to these solved tasks in order to define the new task of interest. In the previous example, this was an OR compositionality, meaning that we were taking the maximum over subtasks. We can again define an auxiliary task which relates these solved tasks to the task of interest. There's a new reward function kappa, and a similar result showing that the solved tasks, Q functions, can be added to an auxiliary task to yield the task of interest. Note that we use a zero-shot solution on the left-hand side by applying the same function of composition to the Q functions, and then we add on some auxiliary correction. In general, we have that K and Q tilde share the same optimal policy, meaning again that we have pi tilde star is equal to pi K star. So one can solve either the auxiliary task or the task of interest, and they'll still have the same optimal policy. We note that this function K generalizes this C infinity divergence correction function from the work of Hunt et al. Using the subtasks shown earlier, we find that the corrective value function is much easier to learn than the composite task. In this work, we've shown that two arbitrary tasks in Entropy-Regularized RL can be related by a third auxiliary task. This insight has led us to results on transfer learning, reward shaping, compositionality, and different transition dynamics. This information allows previously collected solutions to be used by the agent and speed up learning. We've shown that learning K star, the corrective value function, instead of the task of interest directly, considerably improves the training time. We can also learn the generalized version of a divergence correction for arbitrary compositions of tasks.